Hello and welcome to my talk. My name is Rossen Stoyanchev. I'm a committer on the Spring Framework team. Last year, I gave a talk introducing reactive programming, and I'm very honored to be back this year to talk about the two web stacks that we have in the Spring Framework 5, and we're just weeks ahead of GA. It's been a long journey, but we're almost there. I want to start with a quick disclaimer. You may not know anything about reactive. If you haven't done anything in the space, you might need to complement a little bit with some other talks. In addition to this, it's a bit of a tricky space. It can be a little bit of a challenge to catch up unless you actually try it. But the good thing is that we're going to take a look at some examples. So you should be able to follow along for the most part if you have experience in building web applications and working with a servlet stack. I also want to say that you actually don't have to have a Spring background. You don't have to know much about developing web applications with Spring MVC. My interest is more in showing the evolution of the servlet stack and what most people are using for developing web applications. Again, the syntax that you see, you should be able to follow along as long as you've been building REST and web applications. That shouldn't be too much of a challenge. So again, my interest is in showing that evolution of the servlet stack because there are certain things that we've been doing for a very long time. Over the last 4 to 5 years, one could say that Java has caught up in the productivity area with the rise of full stack frameworks like Spring Boot, catching up to the likes of Ruby on Rails in terms of being able to get up to speed and be productive very quickly. And what I'm going to talk about today is a similar revolution in the execution model that we're using, bringing it on par with the likes of Node.js in terms of having an asynchronous non-blocking foundation and using a kind of a very different approach to getting the most out of the hardware and efficient use of resources. So we'll talk about that. On the left-hand side, you see a traditional servlet stack, including a servlet container consumed through the Servlet API, and then a web framework on top. And then on the right-hand side, you'll see that there are some new non-blocking asynchronous runtimes. Very notably, you have Netty, which is a very widely used asynchronous non-blocking runtime. So for anybody doing much in that space, there's a good chance that this is something that you've looked at or heard about. And obviously, if we have additional runtimes, then we can't really be using the Servlet API on top. And this is an interesting point in itself because the things that I will talk about in terms of the execution model and the use of non-blocking I/O, a lot of that has been happening in the servlet space as well, in the servlet container space, I should say. The likes of Jetty and Tomcat have been innovating and refactoring quite a bit over the quite a few years now to come up to modern workloads and to make a ton of improvements. But what hasn't really happened as much is the programming model on top to catch up, and that's really what we're talking about here. You will notice that in Spring 5, we actually have a name for this parallel web framework to Spring MVC. It's called Spring WebFlux. So we have Spring MVC and Spring WebFlux. And I also want to mention that it isn't just the web stack. I mean, the web stack is very important, but when you develop web applications, you will also be working with data. So there are other efforts that create more of a vertical approach. So you have Spring Data Reactive that's coming out. It's already in late milestone phases. So there's a lot of stuff that you can try out and that we're going to take a look at today. Spring Security already has a couple of milestones. So all of these things that you need to actually run applications. Now, you will notice that what we have next to the Servlet API is something called Reactive Streams. How many of you have heard of reactive streams, the specification? Okay, so this is by now pretty well understood. For those of you who haven't heard about it, it's a specification that's turned out to be extremely useful. It's a very, very small spec, actually, about 4 interfaces that deals in this space with interoperability across components that are built to be asynchronous and non-blocking. So if you have, for example, a Mongo driver, as we will take a look at, if you have a web framework, you have a non-blocking runtime, you can bring those together through reactive streams, and you could be using RxJava or Reactor, different reactive libraries. So first we're going to start by taking a look at the servlet stack. And this is probably going to look very familiar. This is a classic thread per request execution model. This is where we started back in the 90s when the Servlet API was created. And this is, of course, a very kind of synchronous, imperative style API. It's very, very easy and simple to write. And we have, for example, the filter and the servlet contracts, and those return void, which basically means that they're not, they assume that if any kind of blocking needs to be done within them, like calling a database, obviously we're going to have to wait until that's complete, and that's what this method signature implies. Also, there is blocking I/O going on. The input and output stream, when you call read or when you call write, you're going to have to block until that completes. So if you have a really slow HTTP client, that means that it may take a little while before that call returns. So for this reason, we have a thread pool that is underneath the Servlet API, and those are the 2 kinds of things that may block, and we need that thread pool in order to achieve concurrency. So we may block in the application itself, or we may block when reading or writing to the client. And in many ways, the story about what we're talking about here, the whole subject and why we're even talking about asynchronicity and non-blocking, is a story of growing asynchronicity, the use of more asynchronous things that we do in our applications. So we've been using the Servlet API and the Servlet stack for a very long time, and maybe some of you will argue or will have an experience where there isn't really a specific problem, in which case you don't really need to change. So this is not about old versus new. This is about kind of asynchronicity creeping in, that very popular track next door, where a lot of people are. The microservices work that we do kind of changes our expectations, and almost out of the box there is plenty of asynchronicity. And you could argue the Servlet API just wasn't built for that. It wasn't built in the of course you can do asynchronous things, but the more you do of it, the more it becomes a challenge. The model is not set up in the best possible way to make the most also out of the hardware. Now, we do have some things that have happened over time. Obviously, it's been a long time, almost 20 years since the Servlet API was created. So for example, back around 2009, we got the Servlet 3.0 async API, which means that we can call start async on the request, and then we can exit the thread. So we do this particular dance that you will see here, where we're starting out as usual, the thread per request, but then we can say start async, and then we kind of tiptoe out of the thread, meaning that we're going to exit all the way from the filter chain without doing anything, knowing that we're starting asynchronous work. Then we can do some work or wait for an event without holding the servlet container thread. And when that work is done, or when we have an event, we can call dispatch on the async context that the request gave us back. And now we can get back into the call stack and complete the work. So it's a little bit, obviously it wasn't originally created for that sort of thing, but it turns out to be quite effective, in being able to do quite a few things. For example, we, in Spring MVC, we integrated the async API back in the day, 3.2 a few years ago, and it's been quite widely used. It's actually been success, and I point that out because with asynchronicity and non-blocking, it's not always easy or even possible to retrofit, as we will see is the case of non-blocking I/O. But for asynchronous request handling, it's actually worked out pretty well, and it's very widely used. So in effect, what this means is that you can introduce an async boundary between the request handling that the controller does and the servlet container thread pool. You're not holding up the thread while you're doing asynchronous things, which means that you can use reactive clients, like, for example, making HTTP calls or calling a reactive data repository inside the controller, and that works pretty well with a servlet container. At the end of the day, input and output stream are still blocking, though, so you're not entirely, in async non-blocking land. Again, there's a lot of things that you can do on the servlet stack. It's not a completely black or white picture. So let's talk a little bit about concurrency models. This is a common misconception that I've come across, especially in our community, in the Java community, because we've been doing things in a specific way for so long that actually talking about what it means to be asynchronous can be confusing, because asynchronicity is kind of a perceived perception from what we're from some perspective. It doesn't really say how that asynchronicity is achieved. So what you see here is that for a synchronous API, where we know that there may be some kind of blocking, we actually need a large thread pool in order to achieve concurrency. If we're going to be blocking while we're making calls to something, we need a thread, or otherwise we cannot process more of these. And of course, Java makes that quite easy, and you've been doing this for a long time. And so in our minds, a large thread pool is almost synonymous with concurrency. I've seen reactions where, well, if you now go to a fixed small thread pool, how can I be still concurrent, right? But if you think about something like Node.js, they have only one thread, and they still have to be a server-side application. They can handle large amounts of concurrency. So really, what this means is that there are different ways to achieve concurrency. And as it turns out, the model that Node.js, for example, uses, because they have to, is very, very good for kind of efficient use of resources. You're not using as much memory because you don't need as many threads that are effectively parked, just waiting for some kind of event to come back. Let's say you're writing to making an HTTP call, and that call may take a while. So now you're sitting there with your entire call stack and all the memory that holds for that to return. Whereas with non-blocking code, you actually only need a few threads, and when the results of these I/O operations come back, then those worker threads can go round-robin fashion and process these events without requiring additional threads to be allocated. So, if this doesn't make 100% sense, I just want to point it out and put it in your mind that there are different ways to achieve concurrency, and that doesn't necessarily mean that you need a lot of threads. With the synchronous APIs, obviously, it's very easy to program that way. It's very easy to write a single call stack kind of assumption type imperative code. The one on the right-hand side doesn't come as a free lunch. There's actually some work you need to do to achieve that. It's harder to write code this way, but there are benefits associated with that. So what does it take to actually become non-blocking? Well, at the core, you need an event loop. You need some worker threads that are doing the low-level I/O. Like if we talk about an HTTP server, that's what all servers do. At the core, Tomcat, JD, Netty, they all do that. They have an event loop. They handle a large number of connections. And when a particular connection can do stuff like read or write, they will do that. And then when they can no longer do that, then they move on to the next connection. Simplifying a little bit, but essentially it's this kind of event loop-driven processing with a fixed number of small threads. Also, it implies that your architecture is going to be a lot more event-driven. Because if you think about it, you have your application algorithm you can no longer just go from top to bottom imperative style programming. Any of you have written messaging style applications? Okay. So what do we do in event style messaging? We actually split it up. We send messages, and then there's some kind of a queue, and then we're taking things off of that queue with a small number of threads, and we can do parallel processing that way. So this is something that needs to happen also in the application in order to be able to be non-blocking. We need to be much more event-driven message passing style architecture. And we also need a way to actually compose asynchronous logic, because at the end of the day, what we're trying to do is not pass messages. We're trying to write application logic, and we don't want that to be too complex. So we need some means of composing application logic as well. And then as a bonus, in this kind of architecture, when you have a lot of events flowing, actually you begin to have the issue of overflow, and then you need a mechanism to control. If you can push back to the source and say, I'm not ready, it's non-blocking I/O, so maybe you're not able to write, so you don't want the upstream source to be sending any more events at the moment. So let's take a quick look at the reactive stack as well. So with the reactive stack, we have the HTTP server and the event loop. So the processing actually happens on the event loop thread. And this is true for Netty. Obviously, that's kind of the way Netty works. But it's interesting that even for servlet containers, so Servlet API has a non-blocking I/O from Servlet 3.1, which is why we can also build all this on top of servlet containers. We just can't use the Servlet API in the application. So this is going to look very similar. We have a chain of filters, and then we have a web framework at the end. But there is a key difference here is that there's now a very different assumption. Whereas with the Servlet API, the void return value kind of implies that if you have to do any kind of blocking, that's going to be absorbed by the large thread pool of the servlet container. Here, we're actually running on the event loop, which means that it's maybe 4 threads, maybe 8 threads, depending on the number of cores. You're not allowed to block at any time, because if you do, you're pretty much blocking the server. Again, if you think in Node.js terms, we have a few extra threads here, but it's the same principle. We're not allocating extra threads to achieve concurrency. So we have to be non-blocking by default. That's the default assumption now. So in order to achieve that, we have an asynchronous API. You'll see the return value is no longer void. It's a thing called mono void, and mono is a type from the Reactor library. For those of you that may be familiar with RxJava, so RxJava has the single type. It's very similar also to a completable feature in Java 8. The main difference is that mono gives you composability, and it also gives you reactive streams and back pressure, which means that unlike a completable feature with a mono, until there is a subscriber ready to consume the output, no work actually happens. So it has that deferred nature. Also, for non-blocking input, so if we're reading the body of the request, it's no longer the input stream, because that's blocking I/O again. We actually have a Flux data structure. Again, that's from the Reactor library. So we're reading and writing with a Flux. And Flux is a reactive streams publisher also, but it represents 0 to n elements. And again, in terms of RxJava, this would be an observable. So for those of you familiar with RxJava. And I just want to emphasize one more time that in the non-blocking world, when you say get body, or when you say write, you're not actually writing. You are declaring what you will do, because if you think about what you're getting back here is a flux. That's a promise of the data. The data is not yet consumed. And on that flux, you can compose your logic. You can say what should happen next. Very similar to the way you would use a Java 8 Stream API, and you would use operators to declare what kind of logic you want to apply. In the case of Spring WebFlux, we're going to take these data buffers and we're going to deserialize into JSON, from JSON into objects to make those available to the application. But the point is that we're not actually reading, we're not actually writing. So if you think about what happens is that as you make a pass through the filter chain, there's actually two separate phases. And this is, again, this is just kind of the way non-blocking and async works. In the initial pass through the filter chain, we're not actually doing any work. We're declaring the logic for the application, asynchronous style. And then once the whole chain is built, the actual processing begins by the subscriber at the end of the chain, kicking it off by subscribing, and now the data starts flowing. And again, this brings me back to the point about a messaging style, event-driven architecture, except in your application, you're just using observable or reactor flux. But under the covers, you will see that what looks like a lot like messaging application. You have different processing chunks of logic, and then there's data flowing on those monos and fluxes. And just to point out once again, Reactive Streams is an interoperability spec. So Flux, for example, is a Reactive Streams publisher, which means that when you subscribe to it, it's a source of data. It's going to give you some, let's say it's a Mongo driver. It gives you some data. You can actually control how much data comes at you by making a request, and you can indicate how many items should come back to you. And then those items come only if you request them. So that's the concept of back pressure here, dealing with overflow of events. Okay, so let's actually take a look at some code. So I have an application here to demo. I'm going to start. There are different parts to it. So I'm just going to start first with showing you a car repository. And this is using the reactive repository from Spring Data K. Is this visible in the back? Can you see well? Yep, good. So again, you may not be familiar with Spring Data, but it's a really simple concept. You just implement an interface, and that gives you methods that you can use to insert and retrieve data. So for example, you have insert here, you have find all, and what you will notice is that these methods are actually using reactive types. So this is the reactive data support. And I'll talk about the tailable in a little bit. Then I have a Spring MVC or Spring WebFlux. We actually support the same programming model on top with flexible method signatures. So you have a controller method, which is mapped to the /cars URL, and that's a get mapping. And we're going to call the repository and simply return the output of that from the controller, and that's what we want to write the HTTP response with. And if you take a look at the car, this is kind of like a Uber, Lyft application, obviously extremely simplistic. But we have a car with a location, and then each location has a longitude and latitude. And this is a Spring Boot app, and I'm just going to show you quickly. The POM, I am simply using the web starter. So the web starter in Spring Boot gives me the traditional servlet stack with Tomcat, Spring MVC, kind of automatic defaults. And we're going to switch in a moment to WebFlux, which gives us the reactive stack. So let's go ahead and, one last thing here. So on startup, we're going to insert some cars into the Mongo collection. You can see here we're actually using, this is kind of interesting if you haven't seen Flux in action. We're going to generate a range from 1 to 100. And then we're going to map each number into an actual, we're going to create a car out of that, and we're going to generate a random location in the vicinity. And then we're going to save that to the Mongo collection. So let's go ahead and start this. Okay, so once this is up and running, you will see that we are running on Tomcat, and that's the default. It's very easy to switch to another servlet container like Jetty, but by default, we come up with Tomcat. So let's do localhost 80. We're on 81 here. And we're going to get a JSON array back of all the 100 cars and locations that we inserted. I just want to show here the JSON. And let's take a quick look at the output. So what you will see here, this is the Tomcat thread. So this is kind of the Servlet 3.0 async. Again, we're executing here with Spring MVC on Servlet Stack, so we're using the Servlet 3.0 async requests. This is the Tomcat thread. You can also see the reactive streams contract here in action. Because we got a flux back from the controller, Spring MVC will subscribe to that flux. And you can see that it's requesting unbounded, which means give me all the elements you've got. And I'll talk about that in a moment, why that is. But we're then saying concurrent handling started. We're going to leave the response open because we're going to exit all the way from the thread. And now we're going to get all the data back. And this is the thread coming from Mongo, producing the data into the flux. Once we get all 100 of them, we got a kind of a whole array list. And then we're going to get back, dispatch back into the servlet container thread. Again, that's the little Servlet 3.0 async dance. So let's go ahead and change now to WebFlux. And this is the WebFlux starter in Spring Boot. And this is kind of neat. I mean, I actually haven't changed the I haven't changed the code. So the code is exactly the same, but I've switched the stacks, and you will see that underneath now I'm running on Netty. By default, Spring Boot 2 is actually using Netty because that's a better experience out of the box. And this is not to say that Tomcat is not as good as Netty. That's kind of a loaded comparison anyway. That's a lot more complex. But there's certain things around the Servlet 3.0 async and Servlet 3.1 as well that aren't quite as well done, like detecting disconnected clients. There are little things like that, which in the scheme of things aren't that little. But they're more tied to the Servlet API than to Tomcat, really. So we have Netty out of the box. So let's go ahead and execute the same thing here. And same output. If we now take a look at what happened here, very similar, but you're not going to see that whole back and forth with two different threads. It's just the Reactor Netty thread, and then we're subscribing, once again unbounded, and we get all the data back, and that's it. It's a little bit simpler. We're not like switching threads as many times. Okay, so let's recap here. Basically, we think that whether you're on the servlet stack, and there are many existing applications that are going to continue to be on the servlet stack, even if you're writing a new application, you may consider doing that because it's simple enough, to write applications that way, or maybe because you're not ready to go all the way on the reactive stack because the programming model is actually requires you to learn quite a bit more. But one thing that's quite easy to do, which is good for microservices, is that you can call a reactive data repository, and you can do that from the Spring MVC controller, and you return that flux, or we support RxJava, you can return observable as well, and then Spring MVC will know what to do from there and deal with the whole reactive pulling of the data. But here's an interesting question. A flux represents a potentially infinite stream of data, right? So if we give a flux to the web framework, Spring MVC or WebFlux, how does it know actually what to do? Are we going to be writing an infinite stream, or are we going to be writing a collection and sending back a JSON array? That's an important question, actually. We need to know which one of these two is it. Because with the collection, we can actually buffer all the elements and then write it out. Besides, we need to write it as a JSON array. Whereas with the infinite stream, we need to flush after each item to make sure it shows up immediately. There may be some time in between each item. So generally, those two use cases are quite different. So basically, the answer is that we use the media type to determine what you actually intend to do. So for example, if we know that the client or the server, both can indicate a preference, wants to produce JSON, the only way to produce JSON is actually valid JSON out of a collection is to produce a JSON array, right? That's what we have to go with. And because browsers, so if you think about browsers, which may be a common use case here, they don't know how to consume a stream other than server-sent events. So the media type for that has to be text event stream, or otherwise we have to produce a JSON array, or otherwise the browser, we can be streaming, but the browser is not going to get any of the data until we write all of it. So by default, we tend to assume that what you want to do is to write application JSON. That's why you see that there's no back pressure. We know that this is kind of a collection. We ask for all the data to come. We accumulate it in a list, and then we write that out as a JSON array. But it actually is more interesting to see back pressure in action. So this is where we're going to look at the streaming scenarios. And there's a couple of different media types that can indicate streaming. Obviously, one of them server-sent events. But if you're not in a browser, or if you're streaming up to the server, you might use application stream JSON, which essentially looks a lot like a JSON array without the angle brackets around it. So it's just basically a JSON object one line at a time. Pretty straightforward, simple concept, but we kind of have to know which of these cases it is. So what do we do in the case of streaming? Again, we're a little bit different. We're not accumulating into a list. We're going to be requesting from the source of the data to give us some items. And that's going to be a specific number, not saying, give me all you've got. Then we're going to write whatever we get. We're going to flush immediately to make sure that it's immediately seen by the client. And then we're going to keep repeating that, possibly forever. So this is what it looks like. Here we're indicating from the server side that we're going to be sending SSE. Now, interestingly, the way the back pressure works on the servlet stack, so if we're doing this right here on a servlet stack, we have to back pressure against the blocking write. At the end of the day, there's no getting away from the fact that when you write to the response, to the servlet output stream, that's a blocking write. So the only way to implement back pressure in that case is to actually wait for the blocking write to complete, and then ask for the next item, and you just keep doing that. So that's basically your strategy for back pressure. If you keep asking for more items, then they're going to back up, right? So obviously, we have to apply this kind of back pressure, translate into this kind of simple one-by-one back pressure. Servlet 3.1 non-blocking I/O. Well, this is what I mentioned earlier, that unlike the Servlet 3.0 async, with Servlet 3.1 non-blocking, it's actually really hard, impossible to retrofit into an existing ecosystem of frameworks and applications, because it goes so deep into the framework and stack that you can't undo what is already been written as a blocking code. Also, the Servlet API itself contradicts itself. If you go down the path of Servlet 3.1 non-blocking I/O, you have to forget about many parts of the Servlet API. Like you can't call get parameter because that may block trying to read from the request body. So there's all kinds of things like that which practically mean that You can do non-blocking I/O on a servlet container, but not with the rest of the servlet API. So on the reactive stack, we actually adapt to a non-blocking runtime, which means that we can do back pressure all the way to the socket. And that's pretty neat. I mean, you've got, say, the data repository all the way on the right, reactive data repository. Then you have the controller doing some work. Then you have the web framework. And then you have a reactive layer on top of the HTTP server. And you've got back pressure across all of these components thanks to reactive streams. And that's very powerful because if the HTTP client is slow, let's say flaky client over a bad network, we're not ready to write. We have a way of, the non-blocking runtime gives us a way to check for that. We can translate that into back pressure, and that will go all the way to the upstream to say, don't give us any more items because we're not ready to write them. And that's a very powerful mechanism. So let's take a look at that in action. So we're still running here with WebFlux. And I'm going to take the same query, but I'm just going to add a HTTP, a media type. Let's do event stream, SSE. So now we're getting the data back as server sent events. But let's take a look at the, oops, no, I don't want to exit. Over here. So let's see what happened over here. This time, we did a subscribe, and you can see that it's asking for a certain amount of items at a time. And this is the implementation of the reactive library that we're using, in this case, Reactor. It's asking for 31 items to start, and then we're getting 31 instances from the Mongo repository. Then it's asking for 24 more, and we keep going like this. And what's interesting here is that if at some point, obviously this went fast, but if at some point we had to block, we're not holding on to any threads. So the cost of an extra connection at that point is pretty cheap because we're, our whole stack is built to work pretty well with that. So let's switch quickly back to Servlet Stack here. Okay, so you can see we're back on Tomcat. And I'm going to do the same thing. And once again, I'm going to get server sent events. Now, what happened here, you will see that we're going through the reactive streams protocol also, but we're doing one item at a time. And the other thing you will see is that the write is actually performed on a thread, because we're switching from non-blocking library to a blocking write. We don't want to block, in this case, the Mongo thread on which we are trying to make that write. So we have to switch threads as well to ensure that that blocking write can be absorbed with an extra thread to achieve concurrency. That's the strategy for blocking operations. So we do that automatically, which means that in Spring MVC, once again, you can simply return a flux. And then if that's a streaming scenario, we're actually going to apply back pressure against the source. And we're going to do the blocking write to the HTTP response output stream using a dedicated thread pool for that. So you can do reactive stuff, but obviously at the end of the day, your input and output to the client is still blocking. Okay, now reactive remote service orchestration. Let's continue with the demo here. So I'm going to show you the other bits of the application. So this is a car location service that gives me a list of cars and locations. Then there's also a request booking application. And that one is very simple. It simulates a driver. Say, for example, we make a request to a car, and then the driver can respond within a certain amount of time to accept. And you can see here, again, I'm using mono here to simulate a random think time of 2 to 5 seconds for the driver to respond. Obviously, it's going to be more than that, but that's for the demo here. And then I have a front-end app. Let me just start this one while I'm showing the other. So that one is on 8082. And then the front-end app looks like this. So this is a Spring MVC to start application. And it's using the reactive web client. You will see here that it's actually making a call to that URL we've been using /cars. Then it's deserializing to car each item. Then it's taking the first 5 of those, and then it's making a nested operation using flatmap to make a call for each one of those to the other service to actually try and perform a booking, and then whichever comes back first, we're going to take that one. So that's kind of pretty nice orchestration, and we're using a reactive web client, which is pretty smart about using resources. It's not going to use extra threads, etc. So let's go ahead and run that as well. So what I'm going to do is, this one is 8080. Just book me a car, basically. And we have to actually make it a post, an HTTP post. So there is the random think time of 2 to 5 seconds. And if we take a look at the output for the car application, you will see here that it made the calls to get cars, and then it got 5, the first 5, and then it made an attempt to book each one of those in separate HTTP calls, and then the first one to come back. Let's see, which one did we get? That was car number 4. So pretty nice, actually, that we can do something like this. It works with Spring MVC and Spring WebFlux. We can do reactive style orchestration of remote HTTP calls, do stuff like this. And I don't know if you do this sort of thing or how you feel about it, but I think when you do something like that, it's usually a good moment to kind of boast to your colleagues, what you just achieved, because it is cool. So for the 4th use case, reactive request input, this is something that is now Reactive Stack territory only, because while we can do reactive request handling, return a flux on the servlet stack in a Spring MVC controller, it's actually not possible to make the input non-blocking. That's actually quite difficult to achieve, and not really possible without using non-blocking I/O. So we are talking about doing something like this, taking the body of the request, deserialized as JSON or something, maybe XML possibly, and then working with that. So the thing to realize is that when this controller method is invoked, the body hasn't been read yet. This is just a promise to give me the body as that particular object type. And we can turn around and we can do some composition of logic on that, or we can pass it into the reactive Mongo repository here, which then returns a mono void, which is, again, a promise that tells us, did that succeed or did that fail? But again, when we're making a pass through this controller method, we're not actually executing or reading the data yet. We're just declaring what will happen. That's kind of takes some getting used to that thinking. If anybody comes from a Node.js background, that's probably like, yeah, that's the way it works. But for us in Java, that's not the way we're used to thinking. So it takes an adjustment. So an extension of that, which is quite interesting, is, and again, these are scenarios where the non-blocking all the way reactive stack just shines, because it just becomes so easy to do these things. So what I'm going to show you is a service which, well, the car service, right? We inserted a bunch of cars on startup, but what if we could upload these locations into the service, and we're going to consume them, as you can see here, the request body, with back pressure, which means that as we're reading from the socket, we can tell the socket to stop reading if we're not ready to consume the data. And what we're going to do in this case, well, here we're inserting it into a repository. And then we're going to also stream that down. So let's take a look at the code, actually. So for that, I want to make sure that I'm on WebFlux for the car location service, because, again, that's only possible to do on the reactive stack. And I'm going to restart that application. So this is my car location service, and I'm running on Netty. So now what I'm going to do is go to my, I forgot to do something. 1 second here. So back in the car location service app, I mentioned that there is this method with a tailable annotation. So this is for finding cars, and the tailable annotation is support that hooks into Mongo for an infinite collection. So this is a streaming scenario where, as things appear in the collection, I want to see them. So I'm going to switch to using that in my controller. So I'm going to use switch to that method, find cars by, and now I'm going to restart. And you remember before that when I did server sent events, it gave me the 100, and then it finished because the flux completed, and it said there are no more items. But now what we actually want is a streaming. So I'm going to do, let's see if I can get it from here. So now it's actually waiting for more data to arrive, because that's an infinite collection, and that's how we're getting it from Mongo. And then I'm going to show you, easier to get to it here, the upload app. So for this, what I have is, I am, again, interesting to just observe Flux in action. A lot of the operators are very closely aligned to RxJava. So if you're familiar with RxJS or RxJava, Reactor and RxJava are very similar. The way that I would describe it is that Reactor is more positioned to be the server-side Java, with reactive streams first and foremost, and then borrowing a lot of influence from ReactiveX. So here we have the interval operator, and we're going to produce a number every 2 seconds, or an event, if you will. And then out of that, we're going to generate a random car location. And that is a stream. So then we're going to do a post to /cars. We're going to send that as a stream of as a JSON stream, basically one JSON object at a time. We're going to pass the stream into the body method, and then we're going to say retrieve. And now we're going to get the confirmations back. And that's kind of interesting to see on the controller side as well. So on the controller side, this is where we're consuming the stream. We're inserting it into the Mongo repository, and that gives us back, well, you see it here. We get back a flux of cars, and those are the confirmations for each inserted car, right? Because if at some point it stops, we want to know how many were actually inserted. So that's kind of working with stream semantics. So we still have this guy here sitting and waiting. And now I'm going to go back to the upload and get that started. So this is now uploading into the controller on the server side. And over here, so I have one client uploading data into the car location service. Then the car location controller is taking that, inserting it into the Mongo repository with backpressure coming from the socket as we're reading and into the Mongo collection. And then we have another client that's actually pulling down a stream, and as those locations are going into the Mongo collection, we're streaming down again with backpressure. So these kinds of streaming scenarios become very easy to deal with in WebFlux. Okay, so we can stop. And again, we're going all the way to the HTTP server and applying backpressure in both directions. So essentially, on the servlet stack, we can use reactive clients because we have Servlet 3.0 asynchronous requests. It means that we can effectively do asynchronous work in the controller and kind of separate the request handling from the servlet container thread. That allows us to do streaming to the response with backpressure. It allows us to use a reactive HTTP client like the web client in Spring 5. So that's instantly usable in present-day applications with very little effort. It means you don't have to switch wholesale to being reactive and using Flux or observable for everything you do, which is not an easy transition. It takes some time. You know, I haven't seen anybody who said, you know, this was so easy from the start. But when we start talking about reading from the body of the request or any scenarios on that side, you're not going to be able to make that non-blocking. And you're also not going to be able to make the write back to the client. Any input-output through the servlet input and output stream is going to be still blocking, and that's going to require threads. Again, not necessarily a bad thing. You know, if your application scales fine, yeah, you know, it's very easy to fall into the mindset of, you know, this is the new and cool stuff, and that's the way to go now, versus this is the old stuff. Well, if it works, you know, it's actually a lot simpler to write servlet applications because of the imperative programming model. But if you're feeling this kind of pain, if you're already checking out, you know, different frameworks with different execution models, then the reactive stack is 100% kind of in that direction, where you can get a complete reactive stack, non-blocking asynchronous foundation, and all of these scenarios become 100% possible. So with that, I'm going to, this is the end of my talk here. So if there are any questions, I'll be happy to take some now. Yeah? Writing to the database? Assuming you have a non-blocking driver, yeah.
Oh, I see, non-blocking.
Or you could always do it on a thread as a blocking write.
If you had multiple writes, the Spring transactions are sort of tied to a thread.
Yeah, so at the moment, the reactive data repository in Spring Data K has implementations for Mongo, Redis, and Cassandra. There is no asynchronous database JDBC driver. I know there's some work going on from Oracle that was announced last year at Java 1, but that's not out yet.
Yeah, hi. My question is, are you sharing your code on any GitHub project or anything?
Whether I will share the demo code? Yes, I will put a link in the slides and share it. Yeah.
Hey, Rossen, thank you. I was wondering if you could shed some light on perhaps the direction of Spring, whether it's going to continue to support both RxJava and Reactor and Project Reactor moving forward, or are we going to converge on one of the techs eventually?
Okay. So the question is, again, about RxJava versus Reactor and our support. So what we found out is that in order for us to build a reactive web framework, our reactive stack, we need to use a reactive framework. So we chose Reactor for that. Well, because it's closely developed with Spring Framework. There's a lot of collaboration that happened. We actually went through trying to do things, and then they went through evolving their framework. So it was a very symbiotic relationship there. The again, Reactor is built with server-side Java in mind. I think RxJava comes a little bit more from the background of Android and client-side. It's aligned with its origins come from client-side, like RxJS. But then again, the operators are very aligned. So we take all the inspiration, but we don't feel obliged to be 100% ReactiveX in every respect. In terms of the support, so the fact that we use Reactor internally is not an issue. You can do all of these samples using RxJava, and it's actually really not difficult for us to support that combination. We have a bunch of adapters, so we don't even have to directly depend on RxJava in any way. But there are certain areas where we have to choose, like the more functional APIs, the web client, the functional web framework that we have, WebFlux FN that we're calling it, which I did not talk about here. But in those areas, we've chosen Reactor. You can still easily switch to using RxJava from there because using operators. But again, where we can with flexible method signatures, we support RxJava because it actually doesn't cost us a lot of extra effort.
In Spring MVC, you could store your thread context in thread local. Spring Security did that as well. What is the best way to do that with the new WebFlux?
So in terms of replacements for thread local, it's one of those things which is a convenience we've been using because we're executing on a same call stack. Here, the natural model of execution with message passing and non-blocking is that we're actually operating on many different threads and switching all the time. So it's really not easy to achieve that. Reactor has a feature now for context passing. So if you're using Reactor all the way in the application and in the framework, then we can achieve this kind of context passing. But we haven't built the features in WebFlux yet to take advantage of that. So ultimately, part of the answer is we have to look away from these kinds of habits because they're not so easy or possible. But in certain situations, when you can make assumptions about what libraries are used, it may be possible to achieve the same effect. Is there a roadmap? There is actually a ticket that was open that you can find in Jira that summarized all of these questions, like asking specifically for that kind of support. So we're definitely going to look at it, probably get something into 5.0 GA, but again, there are no easy answers, especially if you use different libraries, reactive libraries.
Thank you all for coming. I think Rossen will be around here for a minute if you have any more questions, and I hope to see you all back in the afternoon.